This is a qubit, not a 0 and a 1. Not magic, it's a vector, and in the next minutes I will show you exactly how to rotate it, measure it, and watch it die from noise using nothing but 3 2x2 matrices you already have the math and skills to understand. I've taught many developers quantum, and the first thing that finally makes it click isn't an equation, it's a picture. So here's the deal. Every qubit operation is just a rotation on a sphere. By the end of this video, you will see superposition, control a qubit with a laser pulse, and understand why real quantum computers fail. We will go from Pauli matrices to Bloch sphere to spin-half systems to Rabi control, and lastly errors. Skip this and every quantum algorithm you ever read will feel like black magic. Meet the Pauli matrices. If you're a developer, think of them as Boolean, integer or float of a quantum computer. The primitive types everything else is built from. X is the quantum NOT gate. It flips state 0 to state 1. Boring? Apply it twice, you get the identity. That's because every Pauli matrix is involuntary, its own inverse. They are also Hermitian, unitary, and traceless. Memorize those 3 words, they show up everywhere. And here's the kicker. Together with the identity, these 4 matrices form a basis. Any 2x2 complex matrix, any quantum operation on a single qubit can be written as a linear combination. 4 numbers, that's it. That's the entire space of a single qubit operations. Now the magic. A qubit state needs 2 complex numbers. That's 4 real numbers. But after normalization and dropping a global phase, we are left with just 2 angles. 2 angles, a point on a sphere. That's a qubit. This is the Bloch sphere and is the single most powerful mental model in quantum computing. Notice something weird. State 0 and state 1 are opposite on the sphere, 180 degrees apart, even though they are orthogonal states. In the quantum land, orthogonal means antipodal. A full rotation by 360 degrees doesn't bring you home. You need 720 degrees. That's the spin 1/2 signature. Yeah, the universe is weirder than your debugger. Pauli matrices weren't invented for computing. They were invented to describe spin 1/2 particles, electrons, protons, neutrons, the intrinsic angular momentum that makes an electron behave like a tiny magnet. Want to measure a spin along any direction? Just take a weighted sum of x, y, and z, the eigenvector of this operator. Spin up and spin down along that direction, and they live at exactly the points theta and phi on the Bloch sphere. So here's the punchline. The Bloch sphere isn't a metaphor for spin. It literally is the geometry of spin 1/2. And every Pauli matrix is the generator of rotation around its own axis. X rotates around the x-axis, Z rotates around Z. That's why quantum gates look like rotations. They are rotations. Okay, theory is nice. But how do you physically flip a qubit? You don't type X on a keyboard. You shine a laser or a microwave at it. And what happens next is one of the most beautiful effects in physics, Rabi oscillations. When you drive a qubit at its resonant frequency, the Bloch vector rotates continuously between state 0 and state 1. The probability of measuring state 1 oscillates as this equation, where omega is the Rabi frequency, proportional to how hard you are driving. One day an X gate, drive for exactly pi over omega seconds, a pi pulse. One day Hardeman, drive for half that, a pi over 2 pulse and you land on the equator. Superposition. This is what's happening inside IBM's quantum computer when your Qiskit code says qc.x of 0. It's precisely timed microwave pulse. Quantum gates are physics, not abstractions. Real qubits are fragile. They leak information into the environment. And the most beautiful thing, you can see every kind of error as a deformation of the Bloch sphere. Bit flip. With probability S, the qubit gets X'd. The sphere contracts along Y and Z by a factor of 1 minus 2S. Your information along the X-axis survives, everything else shrinks. For the first flip, Z gets applied with probability S. Now Z-axis information survives, but X and Y collapses. This is the error that destroys superposition, the silent killer of quantum algorithms. For the depolarizing noise, equal probabilities of X, Y, and Z, the whole sphere shrinks towards the center, towards the maximally mixed state. The qubit forgets everything. Here's a fun fact. There is no physical noise process that can squash the sphere into a flat disk. The math forbids it. It's called the no-pancake theorem. Quantum noise is constrained by the laws of probability itself. And this is why you need quantum error correction. But that is a video for another day. Let's lock it in. Pauli matrices, the building blocks of every single qubit operation. Bloch sphere, the geometry, home of every qubit. Spin 1/2, the physical reality the math describes. Rabi oscillations, how we actually rotate qubits with pulses. Errors, the visible deformations of the sphere. If you understand these 5 things, you understand more about qubits than 95% of people who use the word quantum on LinkedIn.